we discussed 3 ways of solving constraints: analytical, procedural, and numerical. This video will focus on a particular type of numerical solver, called a particle solver. Particle systems are used for a wide variety of solvers. In the animation industry, they are commonly used to simulate effects such as smoke and fire. However, they can also be used to solve other types of problems. The system consists of a set of particles that can move according to certain rules. Typically, a particle's movement is dependent on other particles. Each time step, all particles will look at the surrounding particles. They will apply a set of rules to calculate their future position. The particles are then all moved at the same time, in one go. We will look at 2 examples. The Minimise detours example uses a particle system solver. The form-finding example uses a particle spring solver. The solvers automate the process of moving the particles. The overall approach used in the 2 solvers is very similar. However, the rules used to move the particles are different in each case. With these types of solvers, many computations need to be performed. As a result, performance becomes an important issue. For this reason, all computations are done mathematically rather than geometrically. All required data is extracted from the geometry before the solving process starts. This is primarily the coordinates of all the positions. The solver then manipulates this information mathematically without making any changes to the geometry. Only when the solver has completed executing are the geometric positions updated. Let's start by looking at the Minimise detours example. For this example, we will look at how this type of solver can be used to clump together a set of paths. The aim is to reduce the number of separate paths, while at the same time minimizing detours that would have to be taken. Previously, the approach had been researched by Frei Otto, using physical modeling. In this case, the points on the lines are the particles in the particle system. The iterative process involves moving particles towards one another over a number of time steps. For each time step, the solver needs to calculate the position of each particle in the next time step. To do this, the process loops through all the particles. In the diagram, the red particle is the selected particle for which the new position is being calculated. The calculation is broken down into 4 steps. In the first step, the solver looks for neighboring particles. It finds all the neighboring particles on other lines within a certain radius. In the diagram, 7 neighboring particles have been found. In the second step, vectors are generated from the selected particle to the neighboring particles. In the third step, the magnitudes of the vectors are rescaled. The aim is to ensure that the neighbors closer to the selected particle have a bigger impact than those further away. In the fourth step, the particle's movement vector is calculated by simply summing up all the rescale vectors from the previous step. At the end of the time step, the particles will all move by a small amount. Then the process is repeated in the next time step. Here we can see how the clumping process varies over time. A higher number of iterations means that the lines become more clumped. Next we will look at the example for the particle spring solver.